So my project is what makes your heart rate go up the most: running, jumping jacks, shoveling, coaling sweeping, or running up and down the stairs. And so what I did was I did each activity for 1 minute as fast as I could, and then I waited 10 minutes and did it 2 more times. And then my hypothesis was that running up the stairs will make my heart rate go up the most because I'm never stopping, and my heart rate would just go up and won't stop. And so my results were that jumping jacks, the average of my heart rate was 120, and my average for shoveling was 126, and for running up the stairs it was 156, and for sweeping it was 145, and for running it was 154. So the highest was running up and down the stairs by 2. And my hypothesis was right because running up and down the stairs caused my heart rate to go up more than all of the others. And to record my heart rate, I had I had a watch, and I needed a stopwatch. I had a pencil and paper to write down my heart rate, and a shovel, coaling broom, coaling rink, and stairs.
So I did my project on growing crystals out of salt, sugar, and borax. We started out with research like how crystals grow, and we learned that they grow. They're made of molecules and atoms, and they can be made out of different substances, like the salt, borax, and sugar that we use, and they can also be used. They can also be made out of water and carbon. So for our procedure, we used 3 jars like this, and we put different solutions in each jar. And then we hung a pencil over the top and connected hung string into the solution. So for our solution, we mixed 3 cups of sugar to 1 cup of water, 2 cups of salt to 1 cup of water, and then 3 tablespoons of borax to 1 cup of water. In the end, we learned that the borax crystals grew the fastest, and then the sugar crystals grew the slowest. And the sugar crystals took about 4 days to form, the salt crystals took about 2 days to form, and then the borax crystals took about 24 hours to form.
So my project is what's the fastest, and I was testing the speed of lacrosse shots with my eyes open versus eyes closed, and I determined that this with eyes closed gives you a more central number. These are more spread results, and yeah, this ended up, the average of this was faster than the average of eyes closed, and I concluded that your eyes open gives you a harder shot, but eyes closed is more of a less diverse data, I guess.
So my project is about how catnip affects cats, and my focus question was how catnip affects cats. And my hypothesis question is if I spray a toy with catnip, will my cat play with it more than a cat without catnip? Toy without catnip. My independent variable was a toy with catnip versus a toy without catnip. And my dependent variable is the time spent playing with each toy. And my controlled variable is the orange catfit, the orange toy. And the constants is the size, the color, the type of toy, location of test, and amount of catnip sprayed. And the materials were 2 pink identical catfish toys, which are these. The catnip spray, which is this. The clownfish pet toy, which is this. My Tay-Tay, my cat, and my phone. And I wrote down my steps, the procedure, and I use 3 websites to find my information. And the first website taught me why some cats are not affected by catnip, and the second one taught me what is in catnip that makes cats act strange, and my third source taught me what is exactly in catnip and what it does and why it makes cats hyper or relaxed. And my steps were give my cat a toy that doesn't have catnip spray on it, record the cat's actions, and then give my cat another identical toy with catnip spray on it, record her actions, and repeat for 3 days, because that's how much I had to do it. And I made 2 graphs. So Sunday, she played with the one without catnip for 15 seconds, on Monday for 9, Tuesday for 2, and then on Sunday with catnip for 5, Monday for 5, and Tuesday for 4. And then I have 2 pictures. And then Nipolutone is an ingredient in catnip that makes cats go crazy. Nipolutone is an airward analog stereomizers carbonated in mediated synthesization, airway synthesis plant used in TCM. Catnip is a plant and not a drug to cats. The chemicals in catnip bind to the cat's nose, which then travels to the brain. Catnip is an active herb that compounds nipolutone that has a scent that triggers cat sexual desires. Nipolutone is produced by Lepidopteria, which protects plants from herbivorous insects by functioning as an insect repellent. Where am I? Okay. Catnip stimulates sensory neurons, which affects the cat to act strangely when the catnip scent is inhaled. Some cats are not affected by catnip. Elderly cats are not affected by catnip because they lack the catnip gene. Cats less than 6 months are not affected by catnip because they're still young and are naturally playful. And my conclusion is the purpose of this experiment was to see how my cats would react to catnip. Based on the research, I learned that the nipolutone, the chemical in catnip, triggers the cat's sexual desires, which then explains their weird behavior. Therefore, my hypothesis is if I spray a toy with catnip spray, the cat will play with it more than a toy without catnip. It doesn't occur for all cats because some cats don't have the catnip gene. You can also use catnip to calm some cats, like my cat. Elderly cats are not affected by catnip because they lack the catnip gene. Cats less than 6 months are not affected by catnip because they're still young and are naturally playful.
So I'm doing a project about how norepinephrine and histamine affect sleep. Norepinephrine and histamine are both sleep-preventing chemicals, which can be found in food and either be produced or is just in your food. So I tested for 5 nights on a Saturday, Sunday, Monday, and Tuesday, and Wednesday, and saw how these foods could have affected my sleep. For example, on Saturday I had chocolate, and that affected my heart rate right here. Same with bananas, right here. I had norepinephrine on this week and histamine on this day. And my hypothesis was that foods with histamine and norepinephrine would affect sleep, and my hypothesis was correct.
I did my project on LED photosynthesis. I was seeing which color of LED light would best create photosynthesis. My hypothesis was I thought that green would work best because there's so much like green in nature. But when I did my procedure and I got all the information, the white was best and green was actually last. And when I was looking it up, it was because the plants that are green, they don't absorb green, they reflect it. So when I was trying to put the light on the green leaves, the light was basically bouncing off of it, and so it wasn't absorbing the light. And the way I can tell how photosynthesis happens is because when it happens, it creates oxygen, which makes the little leaves rise.
So I did how does water flow rate impact riverbeds? And so here's a video of what that is. The flow rate is controlled by how big the hole is in the milk jug. So
The slow flowing river is a half an inch wide hole, and then the medium flowing river is 3/4 of an inch, and then the fast flowing river is 1 1/4 inch. So that's how it's controlled by the flow rate. So these are the results, and the slow one seems to have gone the deepest, and then the medium seems like to brought up the most sand. So that's a little bit of stream bank erosion. And then the fast flowing river didn't get any sand up at all in any of the attempts. It kind of had rill erosion, which is like little streams of water coming off from the main bank. And then, so I think the fast and medium flowing rivers are the classic braided stream, kind of like this. And then the slow flowing river is a natural straight stream. Yeah, thank you.
For my project, I experimented how Newton's cradle works and what is the height difference when a sphere is added to the released height. My hypothesis was each time I add a sphere to the released height, the sphere located on the end will increase in height, but also decrease, because when I add force, it will make the sphere jump more, but when it falls back down, it could not cause enough force through the stationary spheres. I tested this by measuring each group of spheres 3 times and then averaged them out to get the numbers 0.67, 0.67, and 0.66. After I found out the averages, I took the mode of the group, which is 0.67, and used that to come to the conclusion that when you add a sphere to the released height, the end sphere jumps about 0.67. Now, you may be wondering how Newton's cradle works. Newton's cradle is a device that demonstrates the conservation of energy and momentum. The first cradle ever made was made in 1967 by actor Simon Prebble. The science behind Prebble's invention is rather simple. It has a metal frame with 5 metal spheres attached by wire. Each sphere is positioned so that they are barely touching one another. So when one of the 5 spheres is pulled upward and released, it swings down and hits the 4 stationary spheres. This causes an electric shock to race through the spheres. When the energy bolt reaches the last sphere, it's launched upward. When it comes back down, it repeats the process until there's no longer enough energy to proceed this process. So in conclusion, with each sphere added to the released height, it jumps about 0.67 inches each time. Also, how the cradle works is when the electric shock goes through the stationary spheres, it pushes it upward, and when it comes back down, it repeats the process until there is not enough energy left to proceed. I found my information from Newton's Cradle, Wikipedia.org, and Physical Forces written by Time Life, and lastly, Newton's Laws of Motion written by Nuzella.
In my project, I decided to make popping boba out of your favorite drinks. So for my purpose, I was seeing how Coca-Cola reacts to certain amounts of sodium alginate. And so for my hypothesis, it was see if I added more sodium alginate than usual, the substance would get all thick and clumpy, and it wouldn't form popping boba as well. So when I tried it out, this is the first time you can't make popping boba without sodium alginate because it won't form at all. It was just going to turn into a liquid, and when you try to form it. But for the second time I tried it, it was with 1/8 teaspoons. It was really small, and it didn't turn out well. When I tried it, you couldn't taste anything. It was just there. You can only taste sodium alginate, and you didn't taste the Coca-Cola at all. The second time I tried it, you could taste the flavor, and you could see more color to it. For the third time I tried it, there was more flavor in the boba, and it was a darker color. Yeah. So for the results, the first trial, I used 2 grams of sodium alginate, and the popping boba came out small in an orangish color, which you can see right here. For the second trial, this is what it looked like. It didn't turn as out as well. It was smaller than the first time I tried it. But for the third time I tried it, when I added sodium alginate, it became a thick and clumpy texture, which didn't work out really well. But this is what it looked like. It was when I tried putting it into calcium chloride, it didn't form as well. When I tried it, there was strings that's still attached to it when I tried putting it in calcium chloride. Unfortunately, in the end, my hypothesis was wrong, but it didn't matter how much sodium alginate I added because it still was able to undergo spherification. And I found out that my project was mostly focused on molecular gastronomy, which is a branch of food science that focuses on physical and chemical processes that arise when cooking. Without this, the food industry wouldn't be as successful in its arts because popping boba is mostly used in desserts, and they use a lot of science with this thing. But also, when I was also researching about this, I found out that sodium alginate is made from seaweed and consists of alginate, a negatively charged molecule called a discharge. A positively dissolved, the sodium alginate creates a liquid solution as sodium ions dissociate from the alginate molecules. When sodium alginate is dropped into calcium chloride solution, the alginate molecules bind calcium. Ions can bind two different alginate molecules simultaneously. The solution thickens and becomes a gelatinous substance. To do this project, you need to make sure all your drinks have been cooled in the fridge. It's recommended that you don't use drinks that have low calcium because it won't go under spherification as well. And then you need to make the calcium chloride mix. For calcium chloride, you need to add 1 cup of water to a clean bowl and then add 2 grams of calcium chloride to the bowl and mix until it dissolves. Then you want to make the sodium alginate solution. In the cup part of the blender, add 1/2 a cup of the liquid and measure out the sodium alginate. And then you want to add another 1 cup of the drink, and then you can blend it so it works well. And after you blend the solution, you might want to leave it in the fridge for an hour or overnight. I left it in overnight for one of the trials because the foam right here, it didn't disappear, so I had to wait until it disappeared so I could do this project. After all the foam is gone, use a syringe to suck up a small amount of the solution. And you might want to practice beforehand because, unlike me, I didn't practice and it came out all clumpy when I tried doing it the first time. For materials, you're going to need a plastic syringe, sodium alginate, calcium chloride, sodium citrate, cold tap water, liquid measuring cups, a bowl, 1 teaspoon measuring spoon, blender, and soda, which is recommended. And you can find all these on sciencebuddies.com. That's it.
Hello, my fellow audience. This is my science project, the balloon-powered car, and my hypothesis was if we put less air in the balloon-powered car, then the balloon-powered car would travel 200 centimeters faster because the straw dispensing the air is small and large amounts of air would be too much for it. Materials: block of styrofoam, 2, 4 CDs, 3, a drinking straw, 4, hot glue, 5, 4 glue stick caps. Question: will the amount of air in the balloon-powered car affect how long it takes to travel 200 centimeters? Procedure. 1, I made the balloon-powered car. 2, I either fully or half inflated the balloon by blowing air into it and then attaching it to the car. 3, then distance was the same each time and it was 200 centimeters. 4, I measured the time it took for the car with an attached balloon to travel that distance. 5. I did 5 times for each fully and half inflated balloon. Results: fully inflated balloon. Times in seconds. Time in seconds. Test 1, 5.75. Test 2, 3.95. Test 3, 4.58. Test 4, 6.92. Test 5, 6.09. Average 5.5. Half inflated balloon, time seconds. Test 1, 5.95. Test 2, 4.05. Test 3, 4.03. Test 4, 4.88. 81. Test 5, 4.70. Average 4.7. Conclusion: our experience showed that our hypothesis was right. The smaller amount of air in the half-inflated balloon-powered car made the car go faster compared to full inflated balloon-powered car. My project is better than Rima's.
This is our project. It's called Launch the Toe. Funny. And we have these balls in here, and you launch them. And when you launch them, it can go in the 5 for 5 points, 10 for 20 points, 20 points, and 100 points. And then behind here we have all the prizes. They're little eggs with all the prizes in them. And then, yeah, that's basically it. But
right here I'm doing electroplating with copper. You have the copper over here, and when the electricity is going through it, it's dragging some of the copper onto it. When the object that has the negative, I think, it's getting dragged over there. The electricity is going into it, but the copper is getting stuck on the outside. So then the object will get plated. Right now I'm doing a little like wood, a little metal mouse toy thing. Some objects we've already plated over here. Some coins, some objects that did not work because they were either already plated or they were aluminum. The solution, it's baking soda, copper, salt, and water. Some objects over here that we're going to plate. Electroplating can be used with gold, platinum, rhodium, nickel, and tin, and chromium.
So, we made a giant cardboard hand because we found this book in our library called A Book of Cardboard Box Engineering. And some people have like problems of like lifting big things, like pieces of like wood or logs. So we built this out of things you might find around the house. This is really just like a prototype for something bigger, stronger, like we would use like PVC piping or some sort of lightweight metal. The constraints were that it was fragile and fairly big, and a few of the fingers were fairly hard to pull, and it was fairly difficult to transport. And sometimes like the strings might break or it might come apart. But it still works fairly well, and the only problem is it's not very like it's not the sturdiest. Like it's still sturdy, but once in a while it'll fall over. So this is basically our science project. The requirements were that it needed to be that all the fingers must be able to move, which all of them do, and it must be able to support itself. It was able to support itself, but then we accidentally knocked it over and it kind of bent a little bit. So that was our science project.
My name is Valentina Mendez, and my science project is about the color of light and seed germination. So my question was that does the color of light affect plant growth? And I did research, and it shows that red, blue, and violet light help plants grow the best. So my hypothesis was that plants with the green light over them will not grow as well as the clear light because it does not have a mixture of red, blue, and violet light. And my experiment contains the independent variable, dependent variable, and the control variable, so which is what I will change, what I will measure, and what is constant. So I used radish seeds because those grow the fastest, and I already did the experiment throughout the February vacation, but I kept the results from for now, because they had the same results. So my results were that on day 4, in 4 of the 8 cups, in the clear box, the seeds sprouted. But in the next few days, all but 1 in the clear box started to grow, but still none in the green box. And it wasn't until day 8 that the seeds in the green box until the seeds in the green box have seeds in them. So I conclude that the clear light is more effective than the green light.
So what we have here is a hydroelectric efficiency mill. So with this water coming down, it's kinetic energy, which is then converted by the motor spinning to actual millivolts of electricity there. And with that, so this was inspired by the book A Long Walk to Water, which is a book where people in Africa have to walk like a lot of miles and use a lot of their times to go get water and miss out of education because they have to be at home or walking to get water. But with this, they can generate electricity to power a pump. And Lenora can explain to you how that pump would work.
So this would have to be larger scale, but the electricity could power a pump bringing the water to them. But the problem is they would have to get the water to get this. Now they could only do it once, or while they're in class, they could have pedals. Same idea, just add pedals to the wheel. But with this version, this model, the pump allows the water to go back up and continue the cycle. And there's this other model we have. If you know the different chains on gears on a bike, this is kind of like that. This one's harder to move, but it generates more electricity when you do it. But it's not too good for the water. It is good by spinning it by hand to generate the most electricity total.
This measures the electricity right there. Oh. So this generates the electricity right there. Leonard, do you want to spin that by hand? Because with this one, by hand, it makes a lot of electricity. It makes from 69 millivolts to 156 millivolts. Right now it's at 80 millivolts, 116 millivolts now. So with water, this gets a lot less millivolts than this one does, because it's a little less wide of a length right there. So the water doesn't really have a lot of space to move it. And Lenora can talk to you about how that affects the millivolts.
I think I just did.
What?
I just did.
Oh.
But
no,
yeah.
How it affects it? From being bigger.
The length may affect the amount of energy produced, because when you swing a baseball bat, if you hit it here, it would not go as far as if you hit it on the tip of the bat. So, and I think that's all there is.
So my project is how acids affect the rate of corrosion. So what I was doing is I was determining which acid would corrode a piece of steel wool the fastest, or have the most rust on it after a certain amount of period of time. So what I did was distilled water, drain cleaner, and vinegar. So my hypothesis was that drain cleaner would speed up the rate of corrosion and have the most rust on a piece of steel wool. So what I did is I took the steel wool and I dipped it into the acid, and then put it on a thermometer probe and inside a test tube. And then wrapped it in a towel. I wrapped it in a towel so that the outside air wouldn't mess with the temperature. And then for 10 minutes, every minute and 10 minutes, I recorded the temperature. And then 5 minutes later, I recorded that temperature. And then I took the steel wool out and examined it for rust. So in the end, in conclusion, vinegar won. It had the most rust on the piece of steel wool in the certain amount of time. My hypothesis was incorrect because I thought that the higher the pH level, the higher it is in acid, but it's really the lower the pH level, the higher it is in acid. So that's why vinegar won, because it had a pH level of 3.0. I recorded the temperatures because when I noticed that the temperature was changing, I could tell that a reaction was happening and rust was forming on the steel wool.
This is my project on what makes ice melt fastest. So basically, me and my partner decided that we wanted to melt ice in different substances. So the substances we used were hot water, cold water, room temperature, Diet Coke, and hand sanitizer. The results were it melted fast in the hot water and slowest in the hand sanitizer because the hand sanitizer turned the ice into some sort of phlegm-like material, and the hot water just basically melted it in about a minute, while the hand sanitizer took an average of 52, 53 minutes. Our conclusion was correct, our hypothesis was correct because the conclusion proved us correct, or proved us right. And in the end, I think that ice melt fastest is a natural occurrence, but when you put it to a test, the results might surprise you, or it might just be normal.
So this is my project about the discharge runoff affecting plants. And basically what I did was I made 5 different mixtures and watered them onto 5 different groups. The control is water, and that's right there. And then I have the 10% plant-based, which is right here. The 25% plant-based, and this is all out of 250 mils. And then I have the commercial 10%, 25%. And so basically what I did was I watered them twice a day. And I saw the effects, which is basically Group 3A, which is the 10% commercial detergent, had the most sprouting. And Group 2B had nothing at all. Group 2A had the second amount of most sprouting. Group 1 control had the third amount of sprouting. And, so Group 3B had only 1 sprout, and everything except for Group 2B had at least 1 sprout. So I used alfalfa seeds. The only thing that I did mess up was I forgot to soak the seeds. But I still got the general results. And as you can see, all the different liquids from control to commercial, they look very different.
So I did acids on red peppers, easily obtainable ones. The substances I used were hydrogen peroxide, acetone, citric acid, and vinegar, which are not pure acids because those are hard to obtain, but they have acids in them. So what I did was I bought 4 red peppers, sliced them in half, and then I just poured each acid twice. Half of them were, the bottom row was cooled with 4 ice cubes and the top was just normal. So I put them in there and waited an hour with 15-minute intervals to see what would happen. Acetone ended up doing the most damage, the cooled acetone. It made the pepper weak, and my camera's really bad so you can't see it on the paper, but it did strip some of the color away and made it like almost breakable rubber. I used about half a cup for each container and just set them in there, at room temperature. My house is 68 degrees, so that's room temperature for me, but that's what the normal ones were at. And I'm gonna say the temperature for the cooled ones was about 52 degrees maybe. And I originally wanted to know, when I was thinking of my idea for the project, I wanted to know if citric acid would react on red peppers like stomach acid reacts on human skin, which burns it off. And I wanted to see if citric acid would do the same since it's inside most of them.
Our project is on the soda explosion, and we did this project to see if the Coke and Mentos, the different types of sodas, would affect how high the Coke would go if we added more Mentos in it. And we just used different brands of sodas, so we used Coke, Mountain Dew, and Crush.
And then my question was, how does the type of soda affect the amount of fizz produced by the reaction?
And my question was, how does the amount of Mentos affect the amount of fizz produced by the reaction?
And our hypothesis was that if we add more Mentos, the Coke will go higher. And then because it has more places to touch because it has more, because of the bumps on the Mentos.
And my question was, we think if we add more Mentos into each soda, the Coke will produce the most fizz because it has more carbonation.
And then we did 2 different experiments. So we did one with all 3 different types of sodas, and then we put the same amount of Mentos in the sodas, and then whatever went higher, we used that for our next experiment. When we did the Coke went the highest, so we used that for our main brand of soda for our question 2, which was how does the number of Mentos affect the fizz in the reaction. And then so we did 1, 2, and 4 Mentos, and then the one went up, I think it went up 3, 9, and then 43 because we did our averages. And then we did 3 trials on those, and then we put them into the graduated cylinder, and we put 90 milliliters of Coke in it. And then for experiment 2.
And the Coke went the highest because it has the most sugar in it. So
the Coke went higher because of how much of the Mentos we put in, and because of on the Mentos it has like bumps and scratches if you look at it slowly, if you look at it closely. And then it sticks to it, the carbon dioxide sticks to it, which makes it like the carbon dioxide explode and to go higher and stuff like that.
And if we did this project again, we probably wouldn't use a graduated cylinder because it lost carbonation, and we would probably use different sodas that don't have such a high carbonation level.
Hi, my name is Max Rapone, and for my science fair project, I want to find out how the mass of an object can affect its gravitational pull in space and the speed at which an object is attracted to it. One of the topics I'm interested in is space and gravity, so I based my project on gravity to get a better understanding of how it works in space. For my hypothesis, I said that I think the more mass the object has, the stronger the gravitational pull, and the speed at which the object is attracted to it will increase. The materials I used was a 25 to 30 inch hula hoop in diameter, 1 to 2 yards of fabric. It has to be long enough to stretch across the whole area of the hula hoop, 7 to 10 large binder clips, 2 chairs of the same height, 4 relatively small balls of different masses, marbles, a scale or triple beam balance, notebook or piece of paper, pencil, measuring tape, a marker, and a stopwatch. For my procedures, I first took the hula hoop on a flat surface and covered it with the fabric, making sure that there are no visible parts of the hula hoop and that the fabric isn't evenly placed. I then stretched the fabric out tightly across the hula hoop and made sure that it is evenly distributed and that no areas are less stretched out than the other. Now take the large binder clips and clip the fabric to the rim of the hula hoop while making sure the fabric doesn't get loose. You might need some help with this step. Once there are 7 to 10 large binder clips around the rim of the hoop, make sure to check to see if the fabric has enough tension. This should be tight enough to make an even horizontal line across the area of the hoop, but loose enough so that when I'm placing a ball in it, there will still be a dip in the fabric. Now take your 2 chairs of the same height and place them far enough away from each other so that the rim of the hula hoop is laying on the top of the chair, making sure that the chair isn't interfering with the fabric. Now take your scale or triple beam balance and measure the mass in grams of all 4 of your balls, recording them in your notebook. Now take your heaviest ball and place it in the middle so that it can move towards the center of the hula hoop. Once it is center, take your Sharpie and draw a dot or circle where the ball rests. This will mark where each ball is placed for the test. Once the middle is marked, take your measuring tape and measure from the dot and mark 4 inches, 8 inches, and 12 inches on the fabric to indicate where the marble will be placed for each test. Now that the diagram is set up, place one of your center balls in the middle and a marble on one of the lines. And based on the mass of the center object, the marble will be attracted to it at different speeds. My results came out to show that the baseball, which had the heaviest mass, had the fastest speed on all 3 of the tests. For all 4 of the balls, I saw that the 8-inch mark had a lower speed average than the 4-inch and the 12-inch. The results of my experiment came out to show that the baseball, which is the ball with the most mass out of the 4, had the strongest gravitational pull due to its mass. All the balls created different sized dips, which affected the speed at which the marble was attracted to it. And the balls with the heavier mass created a deeper dip than the balls with the less mass. According to physicsclassroom.com, Newton's law of universal gravitation states that as the mass of either object increases, the force of gravitational attraction between them also increases. If the mass of one object is doubled, then the force of gravity between them is doubled. This proves that the more mass an object has, the stronger the gravitational pull, but the less mass, the weaker the pull, which can make the object attracted to it move slower or faster. In conclusion, based on the results determined from my experiment, I found out that the hypothesis was correct.
Alright, so my project was crystallization methods. So what I asked was, how does the type of salt used to grow crystal affect the amount of crystal grown? So basically, I had done some research and I found that nucleation is how kind of crystals grow. So basically what happens is that molecules will begin to arrange in patterns around a specific point, often a speck of dust or, for example, the side of a jar, and will begin to solidify, creating a crystal solution. So it often happens with different salts, and you kind of need a saturated solution. So my hypothesis was that if I use different salts like Epsom salt, alum, and borax compared to table salt, I would get better and larger and more crystal growth in general. My results were that I had sort of proved my hypothesis because my table salt did grow. It grew the most, but per tablespoon, it actually grew the least because I put half a cup in, even though per tablespoon, it was only 4 grams per tablespoon. While the borax, I only put 3 tablespoons in, and that was the most with 11.97 grams per tablespoon of crystals. Oh, so sorry. So my hypothesis, so it sort of supported my hypothesis because although it was proved correct, it didn't really make much sense because of the fact that the crystals grew different amounts every time I tried to reconduct the experiment. I think what happens is that it's like very unpredictable. Nucleation is just a very unpredictable thing. So I think that it really depends on the conditions, just all sorts of different variables that really have to be like canceled out. So yeah, it's pretty easy. All you have to do is just get jars like these. Salt, different types of salt, like this one was table salt, Epsom salt, alum, and borax. I had gotten some sites that I used, just looked up some research, did some research on different types of salts, like what they're made out of, some of the chemicals that are in the salts. And then you just take hot water, a certain amount of hot water, depending on what recipe you get, what site you get, and you put the salt in and really just cover it with one of these coffee filters and just leave it. They should grow on their own. So like this one is in current growth. I did put a sponge in. Sometimes sponge helps the crystals. You might be able to see that there's like crystal growth. Same with this one. This one kind of grew out of the jars, so that got a little messy. And yeah, that's it.
Hi, my name is Chloe Stanton, and I am doing a project on dancing. My question was, who has a higher heart rate at dancing, older or younger kids? My research, I found out the heart is a muscular organ that is about the size of a closed fist. The heart sits left of center. It weighs between 9 to 10 ounces, and it beats 100,000 times per day. It pumps 8 pints of blood each day, and children pulses are between 43 and 180 beats per minute. Babies start out with a high heart rate and decreases when they get older. My materials was an oximeter. Someone older than me, I used my sister. Dance classes, I take them at Turning Point all year round, so that was not a big deal for me. 2 notebooks, 2 pencils or pens. My procedure was gather materials, get oximeter, use oximeter to see resting heart rate. Then I went to dance class and used the oximeter after the dance class so I could see my heart rate. And then I repeated the steps. My variables were, my independent variable was age, my dependent variable was heart rate after activity, and my control variable was resting heart rate. My constant was length of each class, and resting heart rate. My hypothesis was a 12-year-old, which was me, will have a higher heart rate than my 15-year-old sister. I believe that I'm going to have a higher heart rate because of the background knowledge that I learned that babies have a higher heart rate. So I'm 12 years old, so I'm like younger than my sister. My data is right over here. My conclusion was the purpose of this experiment was to see if older or younger kids have a higher heart rate than at dance. Based on the research conducted, I learned that the babies have a higher heart rate and it slows down as they get older. Then I will have a higher heart rate. The data I've collected proved my hypothesis wrong because you can see on the graphs that there are like lots of higher numbers of the 15-year-old data. In conclusion, by conducting this experiment, I learned that older kids have a higher heart rate. Something that I could learn from is probably changing the week of it because I would be working on dance recitals, but we did 2 weeks of it, so I could average the stuff. I also learned during this experiment that if you have a higher heart rate as resting, you're not as active, but you're still active. And when you have a lower heart rate, you're pretty active.
So I was doing mold growth, and I was seeing which one would grow mold faster, the dry piece of bread or the wet one. I thought it would be the wet one because, well, it's wet and out in the open. But after 7 days, neither one grew mold. I watered the wet one each day with 7 milliliters of water. Well, yeah, no mold grew. And did you know that cheesemakers introduced mold to cheese to make blue cheese? And I think no mold grew because the preservatives.
My science fair project was about seeing if it would work, like if the plants would, if the carrot, the marigold, and the grass would grow using water, salad dressing, bubbly water, Coca-Cola, milk, and Sprite, but only the marigold sprouted at the bubbly and the water. And this sprouted much later, but it's Sprite. But I actually had to make another one because I had to abandon the milk because it got way too moldy. The salad dressing because it got way too gross. So I made another one using wine, beer, bubbly, nothing, and water. They haven't sprouted yet because I guess they didn't have enough time, but they're only marigolds because only the marigolds sprouted here. And that's all. Our project is about volcanoes, and right here I have all the ingredients that I've tested, and it was baking powder, baking soda, salt, and cornstarch. Salt, and all the liquids were seltzer, rice vinegar, white vinegar, and blackberry lemonade. And over here there is like volcanoes that have erupted in the past and may be erupting right now. So this is Kilauea. This is Mount St. Helens. This is Mount Vesuvius. Olympus Mons is the biggest volcano in our solar system. And this is Diamond Head, and I have hiked Diamond Head. And I made this volcano out of paper mache. And if you add as much baking soda as you can, and then you add this, which is rice vinegar and white vinegar, it makes the eruption happen. The biggest explosion in nature is a volcano's eruption. And the volcanoes don't just erupt, they erupt, then they destroy things. This is magnet hockey. The reason we made the game is because I really like to play hockey and I thought I could turn a project into something I love to do. So we made magnet hockey since she liked to play hockey. We have a scoreboard in the ice arena in the stadium and a mushroom trash can. And so you move the puck around by using the player, because the player has a magnet and the puck is the magnet, and then the puck can attach to the player and you can get a goal easier because they're both the same kind of thing and they stick together to get the goal. And the score goes up to 10 and you have 2 minutes. Yeah. And if the score gets to 10, you're done even though you haven't done 2 minutes. Yeah. And if the score doesn't get to 10, and the timer goes off, you're done with the game. The ice arena, well, the rink basically has walls, so it's easier because then you don't want the puck or the plays to fall off. And the F is for Falmouth, and we painted it the colors, but one of the teams are blue and one of the teams are green, so you can play against the other team. And then the ice arena is made out of tin foil, so it would be easier than to slide across the ice. And it's also kind of the same color as ice. So, yeah. Oh, and on the stadium, this side is blue and this side's green. So then all the green fans go on this side and the blue fans go on that side. There's a snack machine in this stadium. Oh, and we made a little sign. Evelyn made the sign. Yeah, Evelyn made the sign that says, "Welcome to Magnet Hockey." And then this is Edward Falmouth, and the stick and the puck and the stick. And then, these are the goals to go in. So the green team will go on the blue because it has blue, and the blue team will have to go all the way to the green over there. Yeah, and then there's a penalty box. And the blue guy got a penalty. And the penalty box is basically, I don't know anything about hockey, but I think it's basically where they rest. So the benches are where they rest, and the penalty box is, say the green guy, say the blue guy went that to the green guy, he would go in the penalty box because he tripped this guy. Okay. And then this, or if you didn't have the penalty box, in lights you would just take a penalty shot. And then you either get a goal or you wouldn't, and then immediately after you shoot the puck, the other player should come in and play again. And
each team has 4 players, so it's equal. Over here is like the judge, basically. And this is like where we'll do like the score and stuff, and you have like this marker and the eraser. And yeah, basically. And there's 4 players, so if you put one in the goal, then there would be 3 players because you need goals. You can choose your player on the game, so you can actually take 2 players because one would be the goalie and one would be playing, or you could just play like one-on-one without a goalie. But basically, there has to be like at least 2 people playing, so like one on that team and one on this team. But if there's like only one person that wants to play, they have to play against like one of us. And then you would have 2 players in the team, so like you would have partner, like me and Riley would be on the same team because one of them has to be goalie and the other one's the player. Yeah. And then if you don't have the player, Riley, or one of us would just be, like Riley said, the player. Yes.
So this is our claw machine. It's called the prize pickup. We have directions here, our pictures, like create and improve, imagine and plan, ask, and forces. We have magnetism, pull, gravity, potential energy, reflections, and the 3 pictures that are from Hat Day, but not this one though. And the hardest part were the windows and the legs. Want them back? And we use these as little prizes when you and we also had this cup. Where's the cup? Where's the cup? And when there's a ticket cup back here. When you get a prize, you drop it back. You drop it back in, and then we'll hand you a ticket from the Hawaiian ticket cup, and you can scan the ticket for more fun playing. And you wait. Did you talk about these? Yeah. And if you want to grab a prize, you have to use this to pick them up. And when you get a prize, you have to pull it up like this. Hold on. Grab it. But I can't get any of them. Okay. And we also have a board here that tells everything that I just talked about. Here's our names that we had. And on the bottom of the prizes there are magnets. Down here we have the legs. Pretty sure you talked about legs. The legs. And we also have directions here. And that's it. We were doing a backyard bird experiment, and we started by thinking about what the steps would be. And then we thought of the question, the materials, and then what we thought would be the hypothesis. So the steps were we needed to research birds, then we needed to research the feeders and the food. The third step is to make a design,
we made a list of materials, and then we built the bird feeder. Next, we thought of our materials. We needed lots of things. We needed food, bottle caps, hot glue guns, popsicle sticks, pipe cleaners, awls, strings, pine cones, sticks, scissors, clips, plastic bottles, and plastic plates. Next, our team worked together, and my team was me and my friend Jack. So first what we did was we thought of the bird that we wanted to do. We did blue jays, and we thought of how it could keep our bird feeder safe away from cats, what it would eat, and where it would stand. So blue jays would stand on either their food or a tray. Then we thought of the idea, and if you can see right over there, then you'll see the one with the big star, and that's the one that we did. We needed 2 tinfoil or plastic plates. Then we needed 4 pieces of string. Last, we just needed something to hang it on. And then we made our material sheet, and that's basically all that's to it. Thank you. My name is Fiona. Thank you.
Hello, my name is Ricky LaRufa, and this is my science fair project. So it's called Make Your Own Cells. So I'm making an animal cell here. So we're going to start up here with the nucleolus. So the nucleolus goes right in the center here. It's very important, holds all the DNA. Then we go to now we go to the nucleolus. Sorry, that was the nucleus. That goes right on top of it. It's overlapped. So the Golgi apparatus, that's going to go up here. Looks like a Wi-Fi symbol, very important. So all these purple dots on the red is ribosomes. Ribosomes are very important and crucial to the cell. They help synthesize RNA. And the red stuff is the cytoplasm. That's going to hold all the organelles in place. The mitochondria up here. Mitochondria is going to go down here. It's very important. Used to generate most of the chemical energy needed to power a cell. A vacuole. Vacuole is used to hold waste products such as water. A lysosome. A lysosome, it's very small. Contains digestive enzymes that's going to help degrade food. Then we have the smooth endoplasmic reticulum, which is used to make cellular products such as hormones and lipids. And then at the bottom here, we're going to have the rough endoplasmic reticulum, which is used in protein synthesis.
Hi, so our project is a game for 3rd to 5th graders, and it's them practicing Punnett squares with leaping frogs. So we have boards set up with the traits, and you can...
Yeah, so we're just having them match up the genotypes of the frogs, and if they do it correctly, they get to bring home a little frog for themselves.
Our project was watching the weather, a pond study since 1993. We did it about a pond called Shiver's Pond. It's next to our school, and we were trying to describe how climate change is affecting the animals and plants that live surrounding the pond. So we measured the water and air temperature of the pond for the past 25 years, and all the 8th graders have been doing this with people from the town government and also teachers from the school. So our procedure, what was our procedure, Kyle?
We
attached our thermometers to a pole and a tree to measure both temperatures. We dunked that pole into the water, waited there for a few minutes, then we read out our temperatures. Taking a weighted bottle, we dunked that in conjunction with the thermometer into the water and made sure to not get any extra air in it, because that would just skew the data.
Yeah.
And we found that there has been some increase, but with the unpredictability of weather, it's really hard to know whether it has changed a lot, a little, or not at all.
Yeah. So as you can see on these graphs that we did, there's an increase in the water temperature from 1993 to 2019. It slowly got higher and higher from around 2016, and then it went higher and higher until the present, where it's currently dropping down because we're going into winter, but soon it will be going back up and probably go higher and higher.
Okay, I'm Colin O'Brien. This is my experiment. So how does the design of a structure affect its ability to withstand an earthquake? So I'm just gonna start at the beginning. So I originally got this from my friend. Well, I didn't get it from my friend. I kind of got the idea from a friend. But like, oh my God. So he said he was gonna do like a bridge and earthquake, or how a bridge withstands earthquake, and I was like, oh my God, I should do a house. So I did a house. I did it, and my friend, he changed to like masks. He's like down there. I originally thought I was gonna do like a house, like an actual like house template. But now I think that's a lot of work. So I just created these like structures right here. One's like a diagonal, one's a cross or an X, and then one's just straight up and down with side supports. So I originally thought that this would it'd come in last, because it's like what rocks and rolls the most, like what moves the most. So I originally thought this was gonna come last because it's like suspension, and I thought this was gonna come in first because it's all rigid. But I didn't take into the account that the higher it is above the platform here, the more like the less the oh my God, the less the the less the movement is affected. So I just said the less. Oh, okay. So the higher it is, the less shaking it has. The lower it is, the more shaking it has. So this came in first because it moved the most here on both tests. And this came in last because it moved the least on both tests. Here's my platform. It's basically just a switch, a battery pack, and a motor with a weight, an off-balanced weight. And so when you turn it on, it shakes. You may not be able to see it, but it shakes. You can hear it. So when you put this on, by these 4 little bolts you have here, it just like go right onto the springs, like that. And then you put the dice up here on the very center. All the models have these circles. So you'd put it inside this circle here, and then you turn it on, and it'd move because of the vibration. And then this one came in was neutral
for all the tests. Here it moved 1 inch, but it's still neutral. Here it may look like it's below that one, but that's just like a mess up. They're the same. And yeah. In conclusion, I thought that this was a really fun project.
My name is Victor Nicole, and I did my experiment on elephant's toothpaste. I started off by doing my poster to mimic some of the elephant designs, like the elephant's trunk and some grass or water. And my hypothesis was the amount of dish soap determines the amount of foam produced by the experiment, and my hypothesis was correct. By 1/4 cup of dish soap produced more foam than the 1 tablespoon of dish soap. To make elephant's toothpaste, you need to have a packet of yeast, or about 1 or 2 teaspoons of original yeast, half a cup of hydrogen peroxide. The amount of dish soap you need, it doesn't really matter. Food dye is optional just to make it a little cooler, and half a cup of lukewarm water. And what you do is you get hydrogen peroxide, about half a cup, and then mix it with the amount of dish soap you're going to use. You should shake it up to mix it to get a better reaction. And then with have an extra cup on hand and fill that with the half a cup of lukewarm water, and then the amount of yeast, 1 to 2 tablespoons or 1 packet of yeast. Then when you mix them together, it will make the elephant's toothpaste.
My name is Brianne Hunter, and my project is candy digestion. We were experimenting with different candies to see how long they took to dissolve in stomach acid. We used jujubes, Sour Patch Kids, and Airheads, and hydrochloric acid, which is the same pH as stomach acid, which is about 1 to 3.5. And we also used lemon juice, and we left it in hydrochloric acid for up to, it took between 40 to 60 hours for it to completely dissolve. And we measured this by poking with a pencil, where it completely just broke it in your hand. And for the lemon juice, it didn't take as long. And I can actually show you pictures of the thing. Okay. Here are the photos. This is with the lemon juice. These are the jujubes with lemon juice, and they were dissolving. These are jujubes in hydrochloric acid, they swell up and turn red. They're Sour Patch Kids, and they look like pickles. It was really gross. And the Airheads actually absorbed all the acid, and it was, yeah. In conclusion, we figured out that it took from anywhere between 40 to 60 hours for candy to completely dissolve in your stomach. So maybe not eat as much Halloween candy as you eat each year.
My project was our different colors of food coloring made from the same molecules. And this was made with my friend Gia, who isn't here, but it was me and her. So our background info for this project was that we would be conducting gel electrophoresis, which is the process of separating macromolecules from smaller molecules. Macromolecules are larger molecules like DNA, RNA, proteins, etc. And they all have nucleic acid, which is how this experiment works. The gel holds the substances in place, and when we apply an electric field over the gel, there's a negative end and a positive end. Because they are negatively charged, they will go more towards the positive end. So we can determine which macromolecules are more positively charged and negatively charged in each food coloring. So our hypothesis was that if we inspected all of the different colors, food coloring in different colors using gel electrophoresis, we would find that the amount of macromolecules in each color is different because they're all made of different pigments. And our variables were that our control variable is, we're doing the same test, gel electrophoresis. Our dependent variable is how many centimeters the dye travels. And our independent variable is the color dye we conduct the experiment with. These are our materials. Our procedure was essentially just creating the chamber and then testing with it. But a more in-depth explanation is we created the gel, we set up the wires to put the electric field over it, and then we placed the colors into the indents created, and we turned on the batteries and stuff, and we waited 30 to 45 minutes to see how far they traveled, and then we ended up with our results. They're really small here, but they're printed larger here. The goal was to kind of see, the goal in gel electrophoresis is not only to separate them from the original substance, the macromolecules, but also to see which macromolecules are more negatively charged and their size. So we found that since blue traveled consistently the farthest, it had the smallest macromolecules and it had the most negatively charged ones, but as opposed to red, which barely traveled, it had the largest macromolecules and the least negatively charged macromolecules. Now the yellow traveled pretty in the middle, but since we did green as our third color, we tested blue again and yellow. So yellow was pretty average overall. Yeah, that was our conclusion. Our works cited is here. In the first test though, the blue traveled consistently farther than all of the other tests, so we think that's due to human error. But in all the other tests, it traveled a lot farther. Well, the real-world application is gel electrophoresis is commonly used in forensics to analyze fingerprints and DNA. We just use DNA, we use food coloring because it's a more household object. But if we ever wanted to complicate it or make it more complex, we could try more colors, inspect the brands, look at the ingredients to see which variable made different colors travel more. And we could try actually using DNA rather than food coloring, or maybe even a different substance.
I'm Keegan Heffern, and I did this project with Jack Collins. Our project is nitrate concentration in Buzzards Bay. Our research question was, how does the moon phase affect the nitrate levels in Buzzards Bay? And if the moon phase has a correlation with nitrate levels, then how do the tides also affect nitrate levels in Buzzards Bay? Our hypothesis was there would be high levels of nitrates in Buzzards Bay within a couple days of the full moon and the new moon of each month. This is because this will be when we have the highest high tide and the lowest low tide. And it'll pick up the excess nitrates, which will lead to a higher nitrate level.
I'm Ian Maxim, and this is Joey Simpkins, and our science fair project is on wind turbine efficiency, and it's called Fantastic Energy.
So what we were trying to figure out with this project is what is the best way to make a wind turbine using the materials that we had available to us. So we changed the angle of the blades, the number of blades we had, the angle that the wind hit the blades at, and the shape of the blades.
So to start this project, we completed some preliminary research in which we found there are two separate types of wind turbines. There's a wind turbine that rotates on a horizontal axis and one that rotates on a vertical axis. And so through our research, we found that the horizontal axis turbine is the most efficient, so we focused on this. And then we also found out that the most efficient way to create a turbine is to increase the tip speed of the blades to make it as fast as possible. And so we predicted through this that a wind turbine with, and we also found out that 4 turbine blades are marginally more efficient than 3 turbine blades.
So based on this research we did, our hypothesis was that a turbine that had 4 blades at a 30-degree angle and that were the rounded shape we made would be the most efficient. As you can see here, we made 3 different blade shapes to test it out, and this was the rounded one that we thought would do the best when we tested it.
So the materials we used, we created our own model wind turbine, which is, here's a picture of it right here. And then we created a bunch of different balsa wood blades, which he just showed off. We used box fans, a voltmeter, which is right down here, and wooden rods to attach to the blades.
So when we were doing this experiment, we first designed the 3 different blade sets that we showed you before. And then next, with these blade sets, we tested each of them at a constant angle from the turbine. And then once we had determined which of the blade types produce the most power, we then tested this blade with a different number of these blades on the turbine. And then we took a running average of the voltmeter readings for each of these trials. And then once we figured out which number of blades was most efficient, we also tested the angle that the wind was at as well as the angle that the blades were at to see how this would impact the power production. And from all of this data that we collected, we were able to determine which turbine would be best.
So as a summary of our first research, we found out that of all the different blade types we tried, a wind turbine that had 3 blades, and that the blades were at a 30-degree angle to the wind, and the blade shape of a rounded shape, which most replicated modern wind turbines, would be the best shape for our project. And this created about 0.221 volts.
Then once we had figured this out, we put the blades at different angles. So we put them at 30 degrees, 80 degrees, 60 degrees, and 90 degrees. And then we moved the fan around so we could get different angles at which the wind would hit the turbine. And then that gave us our data here, which kind of shows that it was best when it was hovering around like straight, hitting the turbine straight on. So when looking at our data, we found that of all the things, a curved blade with 30 or 60 degree angles from the vertical of the wind would be the most efficient. And then finally we determined that the farther away from upwind that you got, either downwind or the other way, this would make the turbine less efficient, meaning that turbines should be created to turn upwards into the wind. And so for some of our experimental limitations, we found that there were some slight irregularities in blade shape, as well as some slight variations in fan distances and some human protractor areas.
Okay, I'm Liz Litton and this is Catherine Walsh. And this is our base pair battle. Basically, we have 2 DNA strands with 1/2 of the nucleotide base pairs filled in, and the object of the game is to race against a partner and fill them in accurately following the rules of base pairing, which is A always goes with T and C always pairs with G. The first person to finish presses the button, and if their entire strand is accurate, then they get a prize. If their strand is not accurate and the second person's is, the second person gets a prize. And if they both get something wrong, we do a tiebreaker round.